We continue with discussions of angular momentum, the forces that are acting when we are considering the angular forces, and also trying to find out the angular momentum that is generated and the balance equations, the total forces and also the forces that are generated through their actions. So in the steady flow, as we have seen, the total forces, external forces, are given by summation of m, as I indicated on the left hand side of this equation, and on the right hand side we see it are given as the integral over the total control volume r cross v into rho into vr dot n, where n is the unit vector normal to the direction of the force times the area on which the forces are acting. An approximate form of the angular momentum equation in terms of average properties at inlets and outlets, because we have to equate them. The total external forces must be equal to the forces that are generated at the devices or the point of application wherever they are being applied. So the external forces equal to a rate of change of r cross v rho into the volume over the control volume. So this is if the flow is unsteady, and that is why d by dt is appearing. If the flow is steady, this term will disappear, because in that case there will be no change with respect to time. Plus the other forces r cross m dot rate of change of mass into the velocity at the outlet minus r cross m dot rate of change of mass into v at the inlet. And then, as I was just saying, that if the flow becomes steady, the term that depends on time variation will disappear, and we will have the remaining terms that are indicated below. Again, it is all the same thing, except the net torque acting on the control volume during the steady flow is equal to the difference between the outgoing and incoming angular momentum flow rates. So the flow rate at the outgoing minus the incoming, and the difference of the two should be equated to the external forces that are being applied. If no external moment exists, then the left hand side will be 0, and on the right hand side we will have the remaining term that appears, and again we have d by dt in case there is change with respect to time. If there is none, it will be 0. So that's what we see here, that in the absence of external moments, the rate of change of the angular momentum or control volume is equal to the forces that are acting at the outlet and then the minus the inlet, and this is differentiation with respect to time. When the moment of the inertia I of the control volume remains constant, the first term, this is a small typographical error, and this kind of things happen normally. It's an inadvertent typing error. So the first term on the right hand side of the above equation becomes simply moment of inertia times the angular acceleration. Therefore, the control volume in this case can be treated as a solid body with a net torque that is equal to inertia of the body times the rate of change of angular acceleration alpha, which is equal to the difference of these two forces. We try to apply these equations or these rules on certain devices. One of them, the very common one that we apply, that we see in our daily life, are radial flow devices. So if there is a rotation that is being given, or because when we are talking to angular momentum or the forces that are angular in nature, then of course we will have two variables coming in: radial side indicated by variable r, and the angle through which the movement takes place, which we denote by normally by theta or some other angular side. So many rotary flows, they are the thing. The common examples of them are, for example, centrifugal pumps and the fans. Both of them are rotating. They are rotatory in nature. The forces that act on them are in the rotational direction, and the application generates the flow that is also angular in nature. So these are the examples where we see these forces are applied in everyday life. Here is a picture, and it has been trying to show that how these equations are applied and how the devices look like. This is just to explain the example and also to make the computation, the calculation, how they are done. So this side is a side view of the centrifugal pump, and this is the frontal view as we are looking at the centrifugal pump. And this we see in our daily life every day. Now in between, you see the parameters that we are talking about, the radial distance and the distances, R cross V, or the fixed, the boundaries, the volumes, the area of cross section, and the volume amount of fluid flow that is coming out of it. If it is water, let's say we are talking about the water. If it is air, we are talking about the air. But you can see the R1 is the distance that is given from this point to this point. Axis of rotation to the boundary, and that is R1. And at the outlet, you can see then this distance is taken as R2. So you can see the radius R1 is taken for this side, and R2 goes up to here. So similarly, there are casing, and the other things are pretty simple to see. Omega is the angular velocity, the velocity with which this shaft is rotating, and it is rotated by the motor that exists in this device, the centrifugal pump. And as we look at it, we will see that as the motor starts to run in, it sucks in the fluid, whether it is air or water or other liquid, and throws out of the pump of the exit. And that is how the motion is taking place. The action of forces is calculated or equated on the basis of the equation that we have seen a little earlier. The conservation of mass equation for the steady incompressible flow is the rate of change of volume at point V1, that is at the entry and the exit, are the same, because the amount of fluid that is sucked in, the same amount is thrown out. So if, for example, the fan is rotating from the inner side, it will suck in the air, and it will be thrown out outside. The sum of air or amount of fluid is again thrown away. So this is the same, the volume. So this is the rate of change that is being taken. And when we try to calculate it, this volume will be equal to the area of cross section times the velocity. That will give the volume of the fluid that is going on. And from this, the other terms are calculated and seen. In the same way, we have another example of a radial flow device whereby Euler's turbine formula is applied, and all the angles and parameters are shown in the picture. They are very clearly self-explanatory.